So here we are going to see wonderful type of questions, and it is going to challenge you. At the same time, you will be able to enjoy all of these questions, because these questions are nothing but the combining the logics which we learned and applying them in a proper situation. I'm sure you are going to enjoy this. Alright, so let's start. The relation ds is equal to dq by t, where S represents entropy, Q represents heat, and T represents temperature, absolute, okay, holds well in which one of the following process? You know that ds is equal to dq by t is holds only for reversible process, right? So it's a pretty straightforward question. Option A is the right answer. Next question. A system is changed from a single initial equilibrium state to the same final equilibrium state by two different processes, one reversible and the other irreversible. Which one of the following is true, where delta S represents the represents to the system or system entropy? Alright, so here we are having, say, PV or TS, whatever. Here having two states, state 1 and state 2, and one of the process is reversible and other one is irreversible. So there are two paths. Through the path, it is going from state 1 to state 2 through different paths. One is reversible and other one is irreversible. It is given that in that case, what will be how their entropy changes will be related. Okay, we already seen that entropy change is a property change. Between two endpoints, entropy change remains same. So here they are talking about two endpoints only. So for both reversible as well as for the reversible process, delta S should be same. So delta S irreversible should be is equal to delta S irreversible. So we can go for option A. Fine. Now process A is irreversible and adiabatic. Process B is reversible and adiabatic. The entropy change in process A and process B respectively are. So we are having a process A which is reversible and adiabatic. In the case of process B, which is reversible and adiabatic. Okay, so how their entropies will be, entropy changes. Okay, since process A is irreversible, I'll go for ds is equal to dq by t plus delta S generation. Since it is adiabatic, dq is gone, but you know that for an irreversible process, delta S generation will be a positive value, so it will be greater than, ds will be greater than 0. Fine. So entropy change is a positive thing. As far as reversible process is concerned, ds is equal to dq by t, and for a adiabatic process, dq is gone, so ds is equal to 0. We have already seen this. So answer is going to be option D, which is positive for irreversible process and 0 for reversible adiabatic process. Positive for irreversible adiabatic process, 0 for reversible adiabatic process. The equation, next question, the equation TdS is equal to du plus PdV is applicable. You know the answer, right? We have seen this also. This equation is applicable for every process, whether it is reversible or irreversible, anything like that. So we will go for option D, to all process and all working substance, perfectly matching. For any process at all, the second law requires that entropy change of the system is. So they are talking about entropy change of the system. We have seen that a system's entropy can increase, can decrease, can remain same. It's only for universe that entropy can never decrease. They are talking about system. So in a system, entropy can increase, can decrease, can remain same. So option D is the right option. Now next question, the equation delta is equal to R ln of P2 by P1 or P1 by P2 determines the change in entropy of an ideal gas for a reversible process which is adiabatic, isothermal, isochoric, all of the above. So we were having three equations to find change in entropy for ideal gases, right? So one of the equation is that Cp ln of T2 by T1 minus R ln of P2 by P1, right? If the process is isothermal, that means T1 will be is equal to T2. We know that ln of 1 is equal to 0. So if it is isothermal, ln of T1 by T2 is going to be ln of 1, that is going to be 0. So we are left with minus R ln of P2 by P1. According to logarithmic property, we can change this to be ln of P1 by P2. Negative sign I am taking inside, as a result P1 will be going on numerator, P2 will be coming on denominator. So this is nothing but a case of isothermal process. So option B is the right one. For a system undergoing an irreversible process, we know that for an irreversible process, ds is greater than dq by t, right? Or you can write tds is greater than dq. Fine. So option C is the right answer. Next question. If a system undergoes an irreversible adiabatic process, then if a system undergoes an irreversible adiabatic process, you know that for an adiabatic process dq is 0. So dq by t is going to be 0. So option A could be an answer, option B could be an answer. What about an irreversible process? We already seen that for an irreversible process, ds is equal to dq by t. Since it is adiabatic, this will be going 0, but since it is irreversible, delta generation will be there. So as a result, ds will be greater than 0. So we will be getting the option A. Integral dq by t is 0, as well as delta s is greater than 0. Fine. Next is good question. A reversible engine or modified Carnot engine, as shown in the figure, receives 100 kJ of heat at 500 Kelvin and another 40 kJ at 400 Kelvin. Heat is rejected at 300 Kelvin. The work output is equal to. Actually, this is a question from second law of thermodynamics. Do you want me to do, or you will be able to do it? Pause the video and try to do this. So here they have given a cycle, but we can go like this. There is a cycle which is receiving heat from two sources and rejecting heat to a single reservoir. So what are the sources? Sources are at 500 Kelvin and other one is at 400 Kelvin. It is receiving 100 kilojoule at 500 Kelvin and 40 kilojoule at 400 Kelvin. And it is rejecting some heat at what temperature? At 300 Kelvin. It is said that it is a engine, a reversible engine, right? It is a reversible engine. As far as reversible cycle is concerned, you know that cyclic integral of dq by t should be is equal to 0. What they are telling us to find? They are telling us to find what is the work output. Work output is nothing but heat supplied minus heat rejected. Here heat supplied is nothing but 100 plus 40 minus heat rejected. If I know the heat rejected, I will be able to find the answer. How can I find heat rejected? Pretty straightforward. We will apply this equation. So we will be getting 100 by 500 plus 40 by 400 minus q by 300. We have already done similar problems in the second law of thermodynamics. That's why I am going quickly. If you don't know, that means your revision in second law is not proper. So go back first, finish that revision, then only come back to entropy lesson. Alright. Then if you solve this, you will be getting the value of q rejected or q. This is nothing but q rejected. Supply this here, you will be getting that 140 and this is nothing but 90 kilojoule. So it is nothing but 140 minus 90, nothing but 50 kilojoule is the work transfer from that cycle. 50 kilojoule is the work transfer from that cycle. Heat flows between two reservoirs having temperatures 1000 Kelvin and 500 Kelvin respectively. If the entropy change of the cold reservoir is 10 kilojoule per Kelvin, then what is the entropy change for the hot reservoir? So let's draw the schematic diagram here. So heat is flowing between hot reservoir to cold reservoir. Remember, there is no engine in between here, okay? They didn't mention anything like that. They simply mentioned heat is flowing between two reservoirs. One is at 1000 Kelvin and other one is at 500 Kelvin. They said that if the entropy change of the cold reservoir is 10 kilojoule per Kelvin, if the entropy change of the cold reservoir is 10 kilojoule per Kelvin, then what is the entropy change of the hot reservoir? Okay, we know that how to find the entropy change of the hot reservoir, right? Entropy change of hot reservoir is nothing but minus heat transfer, how much of it is losing the heat, right? So minus heat divided by 1000. But I don't know how much heat is transferred. For that they have given a clue that if the entropy change of the cold reservoir is 10 kilojoule per Kelvin, we know that how to find the entropy change of cold reservoir, that is nothing but Q by, this is receiving some heat at 500 Kelvin, which is given as 10. So from here I can find the heat as 500 into 10, that is 5000 kilojoule. So delta S change of hot reservoir is nothing but minus 5000 divided by 1000, that is going to be minus 5. Clear? So minus 5 kilojoule per Kelvin is the right answer, that is option B. Next is a certain amount of fluid at temperature T1 is mixed with an equal amount of the same liquid at temperature T2 in an insulator containing with the total fluid as a system. Consider the following statement. They are talking about energy is conserved, entropy is conserved, entropy will be increasing, energy will be decreasing, and so on. But you know that whatever the process we take, energy is conserved, that is according to first law of thermodynamics. So no doubt we can go for the first statement, energy is conserved. But about entropy, that's what we are going to do. When two fluids were mixed, what is going to happen to the entropy? So consider that here we are having a adiabatic chamber, two fluid 1, fluid 2, okay, at mass m1, mass m2, specific heat of first one is C1, specific heat of second one is C2, and first one is at temperature T1, second one is at temperature T2. Let T1 is greater than T2. Okay, so when I take this partition, what will happen? Both of them will get mixed up. Alright, then if you look at the process, after mixing, both will be attaining at some same equilibrium temperature, say that is TF. So we can certainly say that this TF will be less than T1, because when as far as fluid 1 is concerned, when it is mixing, its temperature will be dropping because it is losing the heat. As far as T2 is concerned, TF will be greater than T2. Fine. So we need to find the entropy change, right? What we will do is that we will find the entropy change of the first mass, first fluid, and we will add up with the entropy change of the second fluid. How will we find that? We know that for liquids and solids, entropy change is nothing but mc ln of T final by T initial, right? That is for the fluid 1. For fluid 2, it is going to be another mc ln of T by initial temperature is T2, and this is going to be m1 C1, m2 C2. Fine, because both are different fluid. So if I want to find the total entropy change, I have to sum it up. So total entropy change is going to be m1 C1 ln of Tf by T1 plus m2 C2 ln of Tf by T2. So here the question is, why we are going to find the total entropy change, and we want to find whether that entropy change is positive value or greater than 0 or less than 0 or equal to 0. That's what we are going to find. So we can do this, but for convenience, let's take that both are having the same mass. Both are having the same mass and both are same liquid. So C1 is equal to C2. But definitely T1 is greater than T2. That condition remains same. Now let's apply these conditions there, then we will be able to get the equation as mc ln of Tf by T1 plus mc ln of Tf by T2. Fine, that is the total entropy change. Now what will I do? I will take mc as common. I will be able to get ln of Tf square by T1 T2. This is the total entropy change. Fine. Now I don't know what is Tf, right? I don't know. I'm just taking arbitrary value as Tf. So I need to find what is Tf. Then only I will be able to conclude whether mc ln of Tf square by T1 T2 is a positive quantity, negative quantity, or equal to 0. So let's find that. For that purpose, we can go for the concept that heat lost by the first fluid is equal to heat gained by the second fluid. So we can write mc T1 minus Tf is equal to mc Tf minus T2. This is nothing but heat loss by heat gain by fluid is both are equal. So MC cancels out. We will be getting T1 minus Tf is equal to Tf minus T2. From here we will be getting Tf is equal to T1 plus T2 by 2. Fine. Now you may substitute there this value there. But before substituting, let's make some arrangement to this thing. So what is that? I want to take this 2 to this side. From logarithmic property, I can write this as mc ln of Tf by root of T1 T2 whole square. Then I can take this 2 on this side. So let me make use of this area also. So I can take this here. So it will be 2mc ln of Tf by T1 T2. Now we know what is Tf now. What is the Tf? T1 plus T2 by 2. So I will substitute that here. It is going to be mc ln of T1 plus T2 by 2 into root of T1 T2. Here comes the twist. What is that twist? The twist is that this can be written as what is T1 plus T2 by 2? That is nothing but arithmetic mean of T1 and T2. What is root of T1 T2? That is nothing but geometric mean of T1 and T2. And an important concept from mathematics is that arithmetic mean will be always greater than that of geometric mean. So let me rewrite this as ln of am divided by gm. Since numerator is greater than denominator, ln value will be always greater than 0. That means we are getting a delta S value which is greater than 0. Fine. That means what is the conclusion? When two liquids are mixed together, its entropy change will be increasing. Fine. Or its entropy will be, final entropy will be more than the initial entropy. So what we can conclude for this question? When certain amount of fluid at T1 is mixed with other equal amount of same fluid at T2, then what will happen? Entropy will increase, but energy will be conserved. So energy of the system is conserved, that is statement 1, that is correct. Entropy of the system will increase, that is statement 3, that is correct. Option B says 1 and 3 are correct, so option B is the right answer. Okay, let me quickly go through this once again. So what we are doing, we are mixing two fluids, fluid 1 and fluid 2. At we have initially taken different mass and different fluid, but later for convenience we have changed it to same mass and same fluid. So for finding the entropy change while mixing, what I will do, I will consider them separately, then I will mix, then I will take the equation m1 c1 ln of Tf by T1 for the first liquid, and for the second liquid, for finding the total entropy change, I will sum it up. That's what I am doing here. Then I am taking, after that I am taking same mass and same fluid. So mc I can take it as common. I will be getting mc ln of Tf square by T1 T2. This is from logarithmic property. If you are not sure, please refer back to that logarithmic property or discuss with your friends or ask me during the live session. We will discuss about that. Then I am taking T1 common. I mean to in order to take the square common, I am putting T1 and T2 in the square root and taking 2 outside, and after that I can take 2 inside also. I mean on the left hand side. That's why I am getting here 2mc ln of Tf by root of this should be root, okay, root of T1 T2. Then I am finding the Tf value using the concept heat lost by the hot fluid is equal to heat gained by the cold fluid. So mc T1 minus Tf is equal to mc Tf minus T2. From there I will be getting the value of Tf as T1 plus T2 by 2. That I am substituting. I am finding that T1 plus T2 by 2 is nothing but geometric mean, and root of T1 T2 is nothing but T1 plus T2 by 2 is nothing but arithmetic mean, and root of T1 T2 is geometric mean. So I will be getting 2 ln of am by gm. Am is always greater than that of gm. So we can conclude that if two fluids are mixed together, then its entropy change will be increasing, or final entropy will be more than that of initial entropy. Fine? Excellent. Next is a beautiful problem. Alright, look at the question and solve it by yourself. The given figure shows a thermodynamic cycle on TS diagram all the processes are straight lines. The efficiency of the cycle is given by. So here we are having a cycle on a TS diagram, which is nothing but a triangle. They have given the upper temperature as TH and lower temperature as TC, and they are given the direction like this, 1, 2, 3. Okay, they are telling us to find the efficiency. Okay, let me tell you one thing. Efficiency will be applicable only for work producing cycle, right? Not for the work consuming cycles. And you have to understand that all the work producing cycle will be having clockwise direction in TS diagram as well as PV diagram. What is the direction? Clockwise direction. Remember that point, very important. Now we have to find the efficiency of this cycle. If you feel that you can find, pause the video, try to do by yourself. We know that what is efficiency? Efficiency is nothing but net work divided by heat supplied. They have not talked about anything about net work or heat supply. But we know that the closed area inside a TS diagram or PV diagram, any diagram you take, the closed area is representing net work as well as net heat transfer. I have already explained this earlier. If you are having doubt, just refer back the earlier lectures. I have explained that in a beautiful manner. So just understand that the closed area inside the TS diagram is representing net heat transfer. Also that is equal to net work transfer. So we need net work transfer, right? That is nothing but the closed area. That is nothing but area of the triangle. That is nothing but half into TH minus TC. But what about area of triangle is nothing but this into half into this into the base. This, right? I know TH minus TC, but what is this? So they haven't given. So let me take it as delta S. So that is delta S. Fine. What else is required? Heat supplied, right? So here comes the twist. Can you find what is the heat supplied here? We have seen that to the system, if we are supplying heat, what will happen to its entropy? Entropy will be increasing, right? ds is equal to dq by t. If the dq is for positive, what is the meaning of entropy change? Increasing. So what we need here? Heat supplied. In order to find in which process heat is supplied, we have to look for the direction of the process. Okay? Then if you are looking at the direction, if you are seeing that entropy is increasing in that process, then we can conclude that in that process heat supply is happening. And after that we will find the area under that, since area under TS diagram is nothing but heat transfer in that process. So if you look at here 1 to 2 and 2 to 3 and 3 to 1. 1 to 2, if you look at here, you can see that entropy is increasing. So it is clear that in the process 1 to 2 heat supply is happening. What about 2 to 3? In 2 to 3, you know that it was initially its entropy is this much, final entropy is this much only, it is decreasing. So heat rejection. You don't have to worry about heat rejection, right? For finding the efficiency, we need heat supply is on the denominator. Again 3 to 1, initial entropy is this much and final entropy is here, decreasing. So heat supply is happening at only one process, that is 1 to 2, because in that process only entropy is increasing. So we need to find an heat transfer or area under that process, that is 1 to 2. And this area we need to find. So we know that how to find that. That is nothing but TH. This is the entire length, and area of rectangle is nothing but area base into length into breadth. So this we already taken it as delta S. So I'll substitute the area of that as nothing but TH into delta S. Delta S cancels out. We will be getting half into TH minus TC divided by TH. You will be getting the answer as option B, that is 0.5 into TH minus TC by TH. So let me quickly give you a revision of that problem. We needed to find the efficiency of that cycle. Efficiency of that cycle is nothing but net work divided by heat supplied. Net work divided by heat supplied. And the closed area will be giving you the net work in a TS diagram as well as PV diagram. So I am finding the closed area, that is nothing but half into base into altitude, that is nothing but half into TH minus TC. They haven't given what is the base, but I am taking delta S as the arbitrarily base. After that, we needed to find heat supplied. That is a crucial step here. Why it is crucial step? We need to figure out in which process heat supply is happening. And we know that whenever heat is supplied to the system, its entropy increases. So we will look for the process in which entropy is increasing in order to find the process in which heat supply is happening. So we can see that only for 1 to 2 process entropy is increasing. So that is the process where heat supply is happening. So we find that heat transfer is happening through 1 to 2. Then how much heat is supplied? We will find the area under that. That is nothing but entire this rectangle. So that area is nothing but length into breadth. So that is going to be TH into delta S. So I am supplying here delta S. Delta S cancels out. We are getting half into TH minus TC by TH. Beautiful problem, right? Excellent. A system of 100 kg mass undergoes a process in which its specific entropy increases from 0.3 kJ per kilogram Kelvin to 0.4 kJ per kilogram Kelvin. At the same time, the entropy of the surrounding decreases from 80 kJ per Kelvin to 75 kJ per Kelvin. The process is. So they have given change in entropy for the system as well as for the surrounding. Then they are telling us to find what is the nature of the process. That means whether the process is possible or not, whether it's reversible or not, whether it is irreversible or not. Alright, you know that according to principle of increase of entropy, right, that is delta S of universe should be always greater than or equal to 0, right? If this condition satisfies, then only any process is possible. That means delta S of system plus delta S of surrounding should be greater than or equal to 0. If it is greater than 0, we will say that that process is possible but it is irreversible. If it is equal to 0, we will say that the process is possible and it is reversible. If it is less than 0, we will straight away say that that process is not possible. So let's find that. So for the first one, it is 0.3 to 0.4. So the change is going to be 0.4 minus 0.3, that is 0.1, plus second one 80 to 75. 75 minus 80 is going to be minus 5. So this value is coming to be less than 0. So the process is impossible, right? Yes or no? Actually, this is wrong. Why this is wrong? Because both are not in the same units. If you look at the option, this one, for the first one it is specific entropy. For the second one, for the system it is specific entropy. For the surrounding it is total entropy. So if you need to add something or subtract something, it has to be in the same units, right? So we had to convert them into same units. So let's convert the first one, specific entropy to total entropy, by multiplying with its mass. As simple as that, right? So it is 0.3 to 100 and 0.4 to 100. So it is going to be 300 and 400 kilojoule per Kelvin. So 400 minus 300, 30 and 40 kilojoule per Kelvin. So 40 minus 30 is going to be 10. That is the system entropy. And surrounding entropy is going to be 75 minus 80, that is minus 5, going to be plus 5 kilojoule per Kelvin. This is also in kilojoule per Kelvin. This is also in kilojoule per Kelvin. This is in kilojoule per kilogram Kelvin. That we are converting into kilojoule per Kelvin by multiplying with the mass. That's what we are getting here. Alright, I'm sure everybody understood that. Let's go to the next problem. Two polytropic processes undergone by a perfect gas are shown below in the pressure volume coordinates. So 1 to 2 process is following a polytropic process with a polytropic index of 1.2, that is PV raised to 1.2 is constant. Process 1 to 3 is a polytropic process with a polytropic index of 1.5. Okay, so that is PV raised to 1.5 is constant. Now we have to convert this PV diagram into corresponding TS diagram, and we have to select the correct option from the 4 given options. Let's see. Okay, so here we are having a PV diagram with PV raised to 1.2 is constant, and this is PV raised to 1.5 is constant. So this is 1 to 2, this is 1 to 3. Fine. So we need to figure out the corresponding process in a TS diagram. Alright. Now, what do you think? One thing is for sure, both the processes are expansion process, right? Pressure is decreasing, volume is increasing. That means it is expansion process. From that we can conclude that temperature will decrease. So look at the options and see, do you getting any ideas? If you look at any of the option, all the 4 options are having temperature decreasing. So that will not help you. Then we have to look for the entropy. In some process, both the process its entropy is increasing. In some process, both the process entropy is decreasing. In some process, one of the process entropy is increasing, other process entropy is decreasing. So entropy is the key here. We need to figure out which process entropy is increasing or both the process entropy is increasing, like that. That is the key here. So for that purpose, we have to find the entropy change corresponding to each process. Alright. Since it is a polytropic process, we know that heat transfer in a polytropic process is given by P1 V1 minus P2 V2 divided by n minus 1 into gamma minus n divided by gamma minus 1. Why we are going for heat transfer? The clue is obvious. You know that whenever heat is supplied, entropy will be increasing, right? Also, we can write dq is equal to TdS, right? So we can write this as TdS is equal to P1 V1 minus P2 V2 by n minus 1. Instead of P1 V1, you know that P1 V1 is nothing but Mr T1. P2 V2 is nothing but Mr T2. M and Mr are constant here for a given process. M is constant, R is also constant. So I am taking Mr outside, T1 minus T2 I am taking divided by n minus 1 and gamma minus n divided by gamma minus 1. Now let's take each process, that is first of all we will go for 1 PV raised to 1.2 is constant and analyze this, okay. For the first process, if you look at this equation, what is this? T1 minus T2. Is that a positive quantity or negative quantity? See, P1, this is T1 will be here, T2 will be here. You know that it is an expansion process. T2 will be less than that of T1, right? I told you that in an expansion process, temperature decreases. So T1 minus T2 is going to be a positive quantity. Okay. Now, n minus 1. N is nothing but 1.2. 1.2 minus 1 is nothing but again a positive quantity. Now comes gamma. So in the question it is given that which process is undergoing? Air is undergoing this process, right? For air, we know that gamma is nothing but 1.4. We can take it as 1.4, right? So 1.4 minus 1.2. What is that? Again, that is a positive quantity. What about 1.4 minus 1? That is also a positive quantity. So what we are getting? Positive. Anyway, Mr is a constant value, that's a positive. Positive into positive divided by positive, positive. So everything is positive. So we will be concluding that for the first process, TdS is greater than 0. Anyway, T will be greater than 0 only. It results in ds is greater than 0 or S2 is greater than S1. So for the 1 to 2 process, we can conclude that entropy is increasing. That is sure. What about 1 to 3 process? Let's see using the same method. Now pause the video and try to do this by yourself. Let's analyze this for PV raised to 1.5 is constant, okay. So again, in this case also T1 minus T2 is going to be positive only because it's an expansion process. T2 will be less than that of T1, so it is positive. N minus 1, N is 1.5, 1.5 minus 1 is also positive, no need to worry. Gamma minus 1, we know that gamma is nothing but 1.4, right? 1.4 minus 1.5, what is it? Negative. Gamma is 1.4 minus 1 positive. So what we are getting? We are getting that TdS, positive into negative, negative, negative by positive, negative only, less than 0, or ds is less than 0, or S2 is less than S1. S2 is less than S1. So what is the conclusion? Entropy is decreasing for 1 to 3, entropy is increasing for 1 to 2, in both the process temperature is decreasing. Just look at different option. Look at option B. 1 to 2 process, entropy is increasing, temperature is decreasing, matching with our speculation, right? Whatever you name it. 1 to 3, entropy is decreasing, temperature is decreasing. So option B is the right answer. See how beautifully we joined different concepts and concluded in this way. Really interesting, right? You might have never thought that we will be ever using this equation, but now it's a time and we are making use of it. That too in conjunction with the concept of entropy. So everything is interconnected. When you are doing these problems multiple times, you will be getting complete command over not only the problem as well as the concept also. By doing the problems only, you can learn the concept of thermodynamics properly. Then it will become like a you will become an addict to thermodynamics, just like what happened to me. I was just a average or below average student, and when I got a year in thermodynamics, but now thermodynamics is my favorite subject. Just because I put effort, I started to understand its beauty. Thereafter, I fall in love with thermodynamics. Alright, let's go to the next question. Wow, beautiful. An ideal gas undergoes a thermodynamic cycle in which when represented on TS diagram is a circle with a maximum and minimum temperatures of 600 Kelvin and 300 Kelvin. What is the efficiency? So what they are saying, there is a TS diagram and there is a cycle there. The cycle when represented on TS diagram is coming to be a circle with the maximum temperature is 600 Kelvin and minimum temperature is 300 Kelvin. We have done similar problems sometimes back in entropy itself, and from that we found the entropy of that. That was a triangle. This time it is going to be a circle. You have to find the efficiency of this circle with the maximum temperature of 600 and minimum of 300 with a circle. Can you do this? Just refer back the triangle problem and see whether you will be able to do this one or not. So here we have TS diagram with a circle with the maximum temperature of 600 Kelvin and minimum temperature of 300 Kelvin. Alright. They haven't given anything else. It is our duty to figure out all the other things. They're just asking what is the efficiency of this cycle. Now, may I ask you one thing? What will be or what could be the direction of this cycle? Anti-clockwise or clockwise direction? What do you think? It is going to be of clockwise direction. Why I am particularly so sure about it? Because they are asking about efficiency. Efficiency is a concept which is applicable to work producing cycles, right? We never ask efficiency of a refrigerator. We ask efficiency of a cycle or a heat engine, right? So you already know that all the work producing cycle is having clockwise direction and work consuming cycle will be having anti-clockwise direction. So it is sure that this is having clockwise direction. Fine. So first part is done. Next, you know that efficiency of a cycle is nothing but net work divided by heat supplied. Correct? How will you figure out the net work? Pretty straightforward. We have seen this earlier, right? That is nothing but the net area, the closed area of the circle will be nothing but the closed area of the circle is nothing but the net work, right? That is equal to net work as well as net heat transfer also. But we are looking for net work transfer, that is nothing but we'll find that. So efficiency is equal to W net divided by heat supplied. It is going to be net area of the circle is nothing but pi by 4 d square, right? Pi by 4 d square. What is the diameter of this circle? 600 minus 300. 300 square. That was pretty straightforward. Now the question is, what is the heat supplied? Can you find that? The heat supplied in this case. How will you figure out? You know the clue, right? The process in which entropy is increasing that gives a clue to us that their heat is supplied. We had done similar problem earlier. So we had to see from which part of the circle to which part of the circle heat is supplied. That is the key. So let me divide entire circle into different areas. I'll say A, B, C, D. Okay. You have to tell me the remaining things. A to B. As the cycle goes from A to B, is the entropy increases or not? A's entropy is here, B's entropy is here. Obviously it is increasing, right? So that is fine. Now B to C. B to C. As the process goes from B to C, what is happening to entropy? B's entropy is here, C's entropy is here. So entropy is increasing. So entropy is increasing. So we can clearly say that as the process goes from A to C, entropy is increasing. What about C to D? C's entropy is here, D to entropy is here, so it is going decreasing. What about D to A? Again, this is also decreasing. Correct? So only thing what we can understand is that for the process A to C, entropy is increasing, so heat is supplied there. So this is the process where heat is supplied. So in order to find the heat transfer under any process in a TS diagram, what we need to do? Just find the area under that, right? So what is going to be the area under that? This entire area. This area of semicircle plus area of this rectangle. That is the area under that curve, right? Area under this curve is entire area under that. So area of semicircle is nothing but half of that. That is going to be 1 by 2 into pi by 4 into d square plus area of this rectangle. So we know that this part is nothing but the diameter itself. So 300. What is the altitude? That is from here to here. So this is the middle of 600 and 300. What is the middle part of 600 and 300? That is going to be 450. So this is going to be 450. So 450 into 300 is going to be this. By solving this, you will be getting the answer. You will be getting it as 0.414. Or in the option we are having 41.5%. Really nice question, right? Of course it is.